Dear learners, today we will discuss circular motion under the chapter Motion in a Plane. Earlier we have discussed projectile motion in this chapter. In projectile motion, the acceleration is constant both in magnitude and direction. There is another kind of two-dimensional motion in which acceleration is constant in magnitude but not in direction. This is uniform circular motion. Generally, circular motion refers to motion in a horizontal circle. However, motion in a vertical circle is also possible. We will learn about them in the following section. After learning this chapter, you will be able to explain circular motion and give their examples. You will be able to explain the motion of a body in a vertical circle. You will be able to derive expressions for velocity and acceleration of a particle in circular motion. You will be able to derive expressions for centripetal force and apply it in different situations of circular motion. Here we are discussing about circular motion. Can you give some examples of circular motion in your daily life? Well, you might have seen the motion of gramophone record, the motion of grinding wheel at constant speed, the motion of hands of an ordinary clock, also the movement of gears, pulleys and wheels. All these are examples of circular motion. Also, the motion of vehicle turning around a corner is an example of circular motion. All these are examples of circular motion in your daily life. Well, the simplest kind of circular motion is uniform circular motion. You might have seen a point on a rotating fan blade. This is an example of uniform circular motion. The motion of artificial satellite in circular orbit around the earth is an example of uniform circular motion. Then what is uniform circular motion? Uniform circular motion is motion with constant speed in a circle. You can see the figure on your screen. Here, suppose the point was at P1 or the particle was at P1 when time was T1. So, the position vector of point P1 is R1. After some time interval, it reaches at P2. Suppose at that time is T2. Now, the position vector of point P2 is R2 and the displacement vector is delta R, which is equal to R2 minus R1. Now, delta R approaches the tangent to the circle at point P1 as delta T tends to be 0. That means, when the time interval is very small, at that time the displacement vector is also very small and the displacement vector tends to be the tangent to the circle at the point P1. As you can see in the second figure, it is the position vector after small time interval delta t is given by the red dotted line and the displacement vector delta r is given by the black arrow, which is the tangent to the circle at point P1. Now, the instantaneous velocity, whenever we are taking the time interval to be very small, we calculate instantaneous velocity. So, now the instantaneous velocity at point P1 is v equal to limit delta t tends to 0 delta r divided by delta t, which is equal to dr by dt. This is the expression for instantaneous velocity v. Now, here are some points to remember. In uniform circular motion, the velocity vector changes continuously. This is because the direction of velocity goes on changing continuously as the particle travels around the circle. Because of this change in velocity, uniform circular motion is accelerated motion, because whenever there is a change in velocity, there is an acceleration. In this circular motion, as the direction of the velocity is changing, the magnitude remaining constant. Hence, we can say that the uniform circular motion is an accelerated motion. And this acceleration of particle in uniform circular motion is termed as centripetal acceleration. Now, let us find out the expression for centripetal acceleration. For this, consider a particle of mass m moving with a uniform speed v in a circle. Suppose at point A, velocity is directed along the tangent ax. Always remember, in case of circular motion, the direction of velocity is tangent to the circle at that point. So, here at A, the velocity is directed along tangent ax. At B, after some time interval delta t, it reaches at B, and here at B, the velocity vector is directed along by, which is the tangent, and delta t is small time interval. R is the position vector at A, r prime is the position vector at B, v is the velocity of the particle at A, v prime is the velocity of vector at B, and delta v is the change in velocity. You can find out this using triangle law of vector addition, and as the velocity vector is along the tangent of the circular path, you can write v is perpendicular to r as tangent is perpendicular to radius at any point on the circular path. So, b is perpendicular to r, v prime is perpendicular to r prime, and hence delta v is perpendicular to delta r. As the average acceleration is along delta v, it is perpendicular to delta r. That means, the average acceleration is perpendicular to delta r. Now, let us determine delta v. Let the angle between the position vector r and r prime be del theta. Then the angle between velocity vector v and v prime will also be del theta, as the velocity vectors are always perpendicular to the position vectors. Now, change in velocity delta v is due to the change in direction. So, now take any point O outside the circle, draw a line OP parallel to and equal to ax or velocity vector v. Draw another line OQ parallel to and equal to by or velocity vector v prime. As the magnitude of velocity vector v is equal to the magnitude of velocity vector v prime, we can write OP equal to OQ. Now, in triangle OPQ, sides OP and OQ represent velocity vectors v and v prime at A and B respectively. Hence, their difference is represented by the side PQ in magnitude and direction. In other words, we can say the change in the velocity is equal to PQ in magnitude and direction as the particle moves from A to B in time delta t. So, now acceleration equal to rate of change of velocity. That means, we can write acceleration A equal to PQ divided by delta t, as PQ is change in velocity, delta t is time interval. So, acceleration equal to rate of change of velocity, that is equal to PQ divided by delta t, that is equal to del v by del t, as PQ equal to del v. As delta t is very small, AB is also very small, because in very small time interval the particle will move very small distance and is nearly a straight line. Now, we can say ACB is a triangle. So, now triangle ACB and triangle POQ are isosceles triangles having their included angles equal, and therefore, these two triangles are similar. So, for these two similar triangles, we can write PQ divided by AB is equal to OP divided by CA. Now, put the values of PQ, AB, OP and CA. PQ equal to delta V, AB is the distance covered in time delta t, that is equal to V into delta t, and OP equal to V and CA equal to the radius r. So, we can write delta V divided by V delta t equal to V divided by r, and by simplifying we can get del V divided by del t equal to V square divided by r. Now, del V divided by del t equal to V square divided by r, but as we know del V divided by del t is equal to acceleration. So, we can write acceleration equal to V square by r, and this acceleration is known as centripetal acceleration. As now we have got expression for acceleration, we can find out the expression for force. As you know that from Newton's second law, force equal to mass into acceleration, that is equal to, now put the value of acceleration, m into acceleration equal to V square by r. So, mv square by r, which is equal to mr omega square, because v equal to r omega, v square equal to r square omega square, r and r cancels out. So, mv square by r equal to mr omega square. So, this is the expression for force, which is known as centripetal force. So, F, the centripetal force, equal to mv square by r, or this is equal to mr omega square, where omega is the angular velocity. This is the magnitude of centripetal force. Now, what is the direction of this centripetal force? Because force is a vector quantity. Now, for that, as delta t becomes smaller, or the time interval when becomes smaller, the angular displacement del theta also becomes smaller. Hence, we can write when the del theta portion becomes smaller and smaller and it tends to 0, at that time angle OPQ equal to angle OQP, which is equal to 90 degree, because here we are taking the del theta angle to be very small or equal to almost 0. So, when these two angles becomes 90 degree, we can write PQ is perpendicular to OP, and as OP is parallel to AX and AC is perpendicular to AX, that is why we can write AC is parallel to PQ. So, from this we can find out that centripetal force at any point acts towards the center along the radius. Some minimum centripetal force has to be applied on a body to make it move in a circular path, otherwise a particle cannot move in a circular path. That is why for moving in a circular path, a centripetal or a minimum centripetal force is always has to be applied on a body, and in the absence of such a force, the body will move in a straight line path. We have already discussed about centripetal force, centripetal acceleration. Now, we will discuss about motion in a vertical circle. When a body moves in a horizontal circle, the direction of its linear velocity goes on changing, but the angular velocity remains constant, or omega remains constant. But when a body moves in a vertical circle, the angular velocity too cannot remain constant on account of the acceleration due to gravity. Acceleration due to gravity affects the angular velocity. So, now let us discuss what happens when a particle moves in a vertical circle. For that, let us consider a body of mass m tied to a string and rotated in a anti-clockwise direction in a vertical circle of radius r about a point O, where O is the center of the vertical circle. Here, in this case, the speed of the body is maximum at the lowest point P, and its speed is minimum at the highest point Q. So, it is maximum at the lowest point P. When it goes or moves upward, its velocity or its speed gradually decreases, because the acceleration due to gravity is acting in downward direction. Hence, it goes on decreasing. When it reaches at the highest point, the velocity is minimum. Again, when it moves downwards, again the velocity goes on increasing. Hence, speed goes on increasing as the body falls from Q to P along the circular path. Now, what are the forces acting on the body? The forces acting on the body at point P, that is the lowest point, are weight of the body mg, which is acting in downward direction, and tension T1 in the string, which is acting in the upward direction. And the forces acting on the body at Q, that is the highest point, are weight of the body mg, which is acting in downward direction, and tension T2 in the string, which is also acting in downward direction. V1 is the velocity of the body at point P, that is the lowest point. V2 is the velocity of the body at Q, that is the highest point. Now, by equalizing the forces as the body is moving in a circular path, and for moving in a circular path, a minimum centripetal force is required. That means, at point P, the centripetal force is provided by T1 minus mg, or the net force acting at point P, which provides the centripetal force, is T1 minus mg. So, we can write T1 minus mg equal to mv1 square divided by r. Simplifying, we get T1 equal to mv1 square divided by r plus mg. Similarly, at point Q, the centripetal force is provided by the net force, and that is equal to T2 plus mg, as T2 and mg both are acting in downward direction. Hence, T2 plus mg equal to mv2 square by r. By simplifying, we get T2 equal to mv2 square divided by r minus mg. Now, what are the speed at the highest and lowest point in a vertical circle? For the body to move along the circle without any slacking of the string, for this condition has to be satisfied, the tension in the string at the highest point, that is T2, must be greater than or equal to 0. That means, the minimum value of tension in the string at the highest point, that is T2 minimum, equal to 0. By putting this value in the equation for T2, that is T2 equal to mv2 square by r minus mg. So, T2 equal to 0, that means mg equal to mv2 square divided by r. From this, we get v2 equal to root over of gr. As we know v equal to r omega, we can find out omega 2 equal to v2 by r, that is equal to root over of g divided by r. At point P, if we find out the speed, now here we put the equation of motion v square minus u square equal to 2as. So, v square, that is the final velocity, is v2. So, v2 square minus initial velocity v1. So, v2 square minus v1 square equal to minus 2g into 2r. Here the minus sign is due to the condition that the particle is moving in upward direction and the acceleration due to gravity is acting in the downward direction. Hence, here the sign, negative sign comes here, and s, the distance travelled by the body, is the diameter of the vertical circle, that is equal to 2r. Hence, by simplifying, we get v1 square equal to v2 square plus 4gr, v1 square equal to gr plus 4gr. Here v2 equal to root over of gr, so v2 square equal to gr. Hence, v1 square equal to gr plus 4gr, that is equal to 5gr. So, v1 equal to root over of 5gr. So, we can find out the angular velocity omega 1 at the lowest point, that is equal to again v1 by r, that is equal to root over of 5g divided by r. Let us discuss the applications of uniform circular motion. From Newton's second law, we can say that as the object in circular motion is accelerating, a net force must be acting on it. Then what is the direction and magnitude of this force? This is what we will learn in this section. Then we will apply Newton's law of motion to uniform circular motion. This helps us to explain why roads are banked or why pilots feel pressed to their seats when they fly aircrafts in vertical loops. Consider a particle moving with constant speed in a circle of radius r. From Newton's second law, force equal to mass into acceleration, and acceleration in a circular path, that is the centripetal acceleration, equal to v square by r. So, we can write the magnitude of force equal to m into a, that is equal to m v square by r. So, this net external force acts on the body when it is moving in a circular path, and it is directed towards the center of the circle. Hence, this force is called centripetal force. So, who provides this centripetal force to the particle to move in a circular path? Well, the centripetal force may be provided by the gravitational attraction between two bodies, as in the case of planetary motion of Earth around the Sun. In case of this planetary motion, the gravitational attraction between the Sun and the Earth provides the necessary centripetal force to the Earth to move in a circular path. Again, the force of friction between two surfaces also provides the necessary centripetal force, as in the case of a vehicle turning around a circular path or moving in a curved path. Here, the frictional force between the tire and the road surface provides the necessary centripetal force. While riding a bicycle and taking a sharp turn, you may have felt that something is trying to throw you away from your path. Have you ever thought as to why does it happen? You tend to be thrown out because enough centripetal force has not been provided to keep you in the circular path. Some force is provided by the friction between the tires and the road, but that may not be sufficient. Hence, when you slow down, the needed centripetal force decreases and you manage to complete the turn safely. So, now what happens when we are moving in a curved path? For that, now we will discuss what is needed to negotiate a sharp turn in a circular path. Let us consider a car of mass m moving with a velocity or moving with a speed of v in a circular path. The force needed to keep the car moving uniformly on the circular path is equal to mv square by r, which is the centripetal force. Here r is the radius of curvature of the curved section. Now, if the road is levelled, the force of friction between the road and the tires provides the necessary centripetal force to keep the car in circular path. But this causes a lot of wear and tear in the tire and may not be enough to give it a safe turn. The roads at curves are therefore banked. Now, what do you mean by banking of roads, and what is the need for banking of roads? Banking means the raising of the outer edge of the road above the level of the inner edge. Roads are designed to minimize the reliance on friction. In some cases, what happens, the frictional force may not provide the necessary centripetal force. For example, when car tires are smooth or when there is water or snow on roads, the coefficient of friction becomes negligible, and when the coefficient of friction becomes negligible, the force of friction may not be sufficient to provide the necessary centripetal force. Let us now analyze the free body diagram for the car to obtain an expression for the angle of banking, which is adjusted for the sharpness of the curve and the maximum allowed speed. Consider the case when there is no frictional force acting between the car tires and the road. The force acting on the car are mg, which is the weight of the car, and Fn, which is the force of normal reaction. The centripetal force is provided by the horizontal component of the normal reaction, that is Fn. Now, let us resolve the force of normal reaction into horizontal and vertical component. Resolving the force Fn into horizontal and vertical components, we get Fn sin theta, which is the horizontal component, and Fn cos theta, which is the vertical component. And what is theta here? Theta is the angle of banking, or the angle by which the outer edge is raised above the inner edge. So, here Fn sin theta equal to mv square by r as the horizontal component provides the necessary centripetal force. And since there is no vertical acceleration, the vertical component of Fn, that is normal reaction, is equal to the car's weight. So, we can write Fn cos theta, that is vertical component, is equal to mg. So, now Fn sin theta divided by Fn cos theta is equal to tan theta, which is equal to mv square by r divided by mg, and that is equal to v square by rg. From here we can calculate the angle of banking theta, which is equal to tan inverse v square by rg. This is the expression for angle of banking theta, which is equal to tan inverse v square by rg. Here in this expression, theta equal to tan inverse v square by rg, we can see that the angle of banking theta depends upon the speed v and the radius of curvature r. It does not depend upon the mass of the vehicle. So, even large trucks and other heavy vehicles can ply on banked roads. Theta should be greater for high speeds and for sharp curves, that is for lower value of r, as theta is directly proportional to v and inversely proportional to r. Driving within prescribed speed limits on curves is necessary. This is all about the banking of roads. Another application of uniform circular motion is aircrafts in vertical loops. On Republic Day and other shows by the Indian Air Force, you might have seen pilots flying aircrafts in loops. Here you can see the figure when an aircraft negotiate or move in a vertical loop. In such situations, at the bottom of the loop, the pilots feel as if they are being pressed to their seats by force several times the force of gravity. Let us understand as to why this happens. Suppose an aircraft is moving in a vertical loop. In that case, the forces on the pilot are weight mg, which is acting in downward direction, and the normal force N exerted by the seat, which is in upward direction. So, what is the net force on the pilot? The net vertically upward force is N minus mg, and this force, that is N minus mg, provides the necessary centripetal force or the necessary centripetal acceleration. So, N minus mg equal to ma. So, N minus mg equal to m v square by r, that is the centripetal force. So, we can write N equal to mg plus mv square by r, which is equal to m into bracket g plus v square by r. So, this is the limit of force for the vertical loop. If this force exceeds the set limits, pilots may even black out for a while, and it could be dangerous for them and for the aircrafts also, because it can cause accidents. Now, let us summarize what we have discussed today. I hope you have understood what we have discussed today. Wishing you all the best. Thank you.